Hi guys, welcome to our channel of Sciences and Mathematics. Today we're going to do with a topic, we're going to do of course a topic in mathematics that is concerning multiplication of matrices. Last discussion on one of our videos we talked about 1 by n matrix that we defined as a vector. Now that we have this concept of multiplication, we're going to look at the behavior of matrices. When of course we multiply two vectors and try to see which kind of rows or categories of vectors behave in a different way and what kind of products we're going to find. So for that case, thank you and welcome. So in this case, we're going to use general examples and then we shall use specific examples in trying to find what are the products that we find in matrix multiplication. So for matrix multiplication, I've said that we had defined a matrix with a single column or row as a vector, and we had given an example like suppose our matrix is A, that is a 1 by n matrix, then we can define that one by this is A11, A12, A13, A1n. So in this case, for a matrix that is represented like that, and then M1, which is of course A11, this is this is 2, 1. This is row 2, column 1, A31, A. This is M1. So these two specific representations that we have talked about is what we referred to in one of our videos as vectors. So basically, these matrices that appear to have that kind of order is what we call vectors. So in this case, these are vectors. Specifically for the first one, these are vectors of the size m or n, and they can just be given. We say that a vector is a quantity with a magnitude and direction. So any representation of that kind of a vector, then we can write that if A is given as a representation for a vector, and we can give it as A1, A2, AN. So for a vector of magnitude n, then we can be able to represent it as such, or size n, we can be able to represent it as such. Similarly, for a vector B, and we can be able to give it a general representation as B1, B2, Bn. So for a vector of size n, then basically this is going to be the general representation for that kind of a vector. And the dot product of A and B, vector A and B, will be denoted as A, B. So this is known as the dot product of the two vectors. This implies the dot product of vector A and B. And this dot product for vector A and B, of course, can be obtained by finding the summation of these individual elements, respective elements. So I'm going to give a general representation for giving the dot product of two vectors that are represented on the board. That is vector A and B. So therefore, vector A, as I have illustrated, and B can be given using the elements I've had given. Of course, I can just repeat them. I'd say that vector A will be represented as A1, A2, AN, and vector B can be represented as B1, B2, Bn. Therefore, dot product of the two vectors can be given as a1 b1. So we multiply, it's a summation of the product of this is respective elements. So this is a1 b1 plus a2 b2 plus an bn. So this the general formula that we're going to use to find the scalar product or the dot product of this specific vectors. So we can give that one a notation by this the summation from I, which is equals 1 to n, as I've written on the board, of A and B from the ith character, from the ith, which is going to give us a scalar, product. So for that case, it's a general representation of how we can find the dot product of two vectors given that A and B have been given those specific representations. So we can use an example in order to illustrate what we are trying to discuss on the board on how to find the dot product of two vectors that we have written. So let A, vector A, be given by 1, 2, 3, and the vector B be given as 2, 0, 1. So in finding the dot product of the two vectors A and B, then this one will be equivalent to 1 times 2. We say we multiply a specific element and then plus 2 times 0 plus 3 times 1. So this is going to give us a scalar quantity which is going to be 5, and that's the dot product of those two vectors. So therefore, generally, given that the dot product of a row and a column, we can be able to determine the dot product for these two specific general representation. So given a row A, now for vector A and B, so given a row A1, A2, AN, and then given a column B1, B2, Bn, we can be able to find the dot product of those two, which is going to be given as A, B is equals A1, B1. We have actually illustrated this A2, B2 plus AN, Bn. So therefore, this is just a repetition of the formula that we have written, which is the summation of, this is the summation of I is equals 1 AI, Bi, which is the dot product of vector A and B. So that's a general representation for finding those dot products. Now suppose we have two vectors which are of course of this specific orders. Let's try to look at this specific example and try to see how that one can be determined or can be able to be defined. So suppose we have a vector A and B, and given that A is equals AIK and B is equals AKJ. Now from representation of course a three-dimensional space, we said that there is a specific order that we represent x, y, z, I, j, k. So for that case, use those symbols. So I hope that we understand when we talk about the concept of I, j, and k as far as vectors are concerned. So for A, let A, I, j, I, k be given as, or be an M by N matrix, and the B, this is basically going to be represented as B, that is lower is for B. So B, K, J be given as an N by S matrix. So the matrix product for A and B, this is AB, is going to be of order MS, that is M by S. So the product for that is going to be an M by S matrix that we can represent as C, which is C, I, J. So you can see that from this respective two matrices, the product is going to affect those representation for the, this is for the IJ and IK, in that the product will be of IJ, which is represented as C. Therefore, this is the CJ, Cij is what we call the dot product of the ith row of A. So C is the ith row of A, and the jth column of B. So remember we talked about the representation of rows and columns for the ith and j respectively. So this is just trying to express the dot product that we find for that. So this one implies that if I have a matrix of order M by N that I'm multiplying with a matrix of order N by S, this is basically N by S, sorry for that, N by S, then I'm going to have a matrix that is of M by S. So basically the aspect of N, that one disappears. Maybe we're going to look and try to see the reason as to why that one happens. But now we can have a general representation for this specific, or it is just a general statement that we have talked about, and give it as the dot product of a vector A and B given as A, K, and B, Kj gives us the product Cij, where Cij is equals Ai. This is the ith row of that one and the jth column of B, as we have said. So that one will give as a summation from K is equals 1 to N Aik and B Kj. So this is a general representation of our application of our matrices A and B, whereby if the number of columns of A is not equal to B, whereby AB implies that actually the number of columns of A, if the number of columns of A is not equal to the number of rows of B, then AB cannot be defined. So in actual sense, it implies that the number of columns of these two matrices must be the same in order for us to perform a multiplication. So we're going to just give an example of that so that we can be able to give an illustration. So in that case, of course, we can just give an illustration of how we can be able to find the multiplication or the product of multiplication of two matrices, so that it will lead us to the general equation that we have given below. So given that matrix A is equals 36, -2, 1, and then 4, 3, 1, 3, -1, 2, and then B is given as 2, 2, 3. This is 1, 5, 1, 1, 7, 1. So those are specific examples for A and B. Then therefore the matrix product for A squared and B, or AB and BA. So we are going to find this matrix product for the letters that I've written and try to see whether maybe specifically these two examples, whether AB is equals BA. So we were trying to define the commutative aspect of multiplying two matrices, whether if we try to commute this one, we can be able to find the same solution. Now for that case, for an A squared matrices, we said that we can only be able to find or define a matrix if the number of column of A is equal to the number of rows of B, and if that is not the case, then that matrix is not defined. So in this case, for this this is a 3 by 3 matrix. Basically the first one is a 3 by 3, and then the second one is a 3 by 3. Now given that we are given a general example for an M by N matrices, and then we said an M by S matrices, and we said for the two, the product is going to be an M by S matrices, and therefore if this is a 3 by 3 matrices, and if this is the case, they are the same, and then this, the answer for that specific matrix is defined. So in this case, we're going to do specific multiplication for the specific numbers of rows and columns. Maybe I can just do away with this 4A and retain that one just for representation. So in that case, we're going to do this by trying to multiply. So we are going to multiply the rows of this times the column of that, as we said that it's the ith rows times the jth column of that one. So it is the first element times 2, which is going to give us now for our A squared, it's going to be this one times, just I can give an illustration, of course, just to draw, give it down here. So this one will be equivalent to 6, -1, 1, 4, 3, 1, 3, -1, 2, times 6, -4, -2, 1. This is 4, 3, 1, 3, -1, 2. So the multiplication of this, we perform it using this order, and then I'll just give after demonstrating, I'll just give a specific answer. So this one is going to be 36 plus, this is 4 times -2, this is going to be 8, so 36 plus minus 8, and then plus, this is 3 times. So you multiply the ith row times the jth column. This is 6 times 6, 4 times 2, -2, 3 times 1, this is 3. So this answer is going to be that 1, 28 plus 3, that 1. So the answer that we're going to find for this case is going to be a matrix of that same order, that MS that we had talked about for that general representation. So therefore, for matrix for the first one is going to be that one, and then performing it for the second one and the second row and the jth column, we're going to have, that is that 1, negative 19, 10, 33, 2, negative 1, 20, negative 11, and 8. So this one, of course, we can just do using the first illustration that I've given by multiplying the first column and the first row and the first column, and then following that specific order, the first and the second, the third and the last, so that we come up with that kind of or a specific kind of an answer. That's for an a by a squared to give us that kind of answer. Now for a and b that we had said, or for b and b, these ones are going to give us different answers, and therefore, as we had requested in our statement to find out whether these two matrices are equal, the answer is going to be different. So therefore, BA is not going to be the same as AB. Therefore, multiplication of vectors do not bear what we call a commutative property, so they are not commutative. So that one you can just work using specific examples like ours here that I've given A and B, but because of space I've just limited that, but shown the procedure on how we can be able to find that one. So in an essence, what we have learned for this is that we have a general formula for representation of multiplication of matrices that I've given on the board, and then we have said that it gives, for the dot product, it gives a scalar quantity, but for the matrix multiplication, that one gives us, of course, a matrix which is a product of ith row and jth column that we gave in that summation formula. So in that case, that's how basically we perform the matrix multiplication of different matrices, or maybe given the vectors that we had started with. And we had said that a vector, of course, by the definition from our previous video, is a matrix with a single column or row. Now, I hope that we have understood the concept for this matrix multiplication. Let's meet in our next videos concerning other examples or illustrations that we may be able to use in order to complement on this. So without further ado, I encourage you to just go to our YouTube channel and subscribe so that we can be getting more of what we have discussed. And maybe try to discuss with us in the comment section so that we can be able to improve our skills in maths and sciences. So bye. God bless you.